Okay, so now we're going to start digging into the new material for kind of the middle section of chapter 14. So last week we learned all about enthalpy, and I'm sure you will all be thrilled to know that enthalpy can be related to stoichiometry. Okay, big word, but you guys are all very familiar now with how to do stoichiometry. Okay, so we can think about the enthalpy that we calculate just as another product or reactant. Okay, if it's an exothermic reaction, energy is given off. So our energy, our delta H, would be listed as a product. If it's an endothermic reaction, energy is being absorbed. So our delta H would be one of the reactants. It would just be listed as a reactant because all the energy is being used up or absorbed. Okay, so if it's exothermic, it's given off. Endothermic, energy is being absorbed or used up. Okay, so if we have a chemical equation and we calculate the delta H, then we can list it just as a product or a reactant. So last week we looked at an example of the decomposition of hydrogen peroxide, and I don't know if you remember, but we had an equation, H2O2, we needed 2 of those in its aqueous form, and if we decompose that, we get 2 waters in its liquid form plus O2 gas. Okay, so hydrogen peroxide decomposing into liquid water plus oxygen gas. And we're not going to go through how we found delta H last week, but it was in the example and it was also in your book. And we found that delta H, or the change in enthalpy for this reaction, is negative 189.2 kilojoules. Okay, so hopefully by now it's starting to sink in. This is a negative delta H, so it must be an exothermic reaction. So energy is being given off. Okay, it's probably going to feel hot. Okay, so if energy is given off, that means that the energy is like a product in the reaction. So we can take this reaction and we can actually rewrite it with the energy as a product. So let's rewrite it as 2H2O2 aqueous. Sorry, it should be a yields 2 waters plus oxygen gas plus, and here we can write in here, 189.2 kilojoules of energy. Okay, so we took our delta H and we wrote it here. Now, why did I change it from a negative to a positive? Well, again, this delta H is telling me that this is an exothermic, that energy is being given off. So by writing it as a product, that's how I'm showing that the energy is being given off. Okay, we wouldn't write negative energy over here if energy were being given off. So whenever we're inserting these into a chemical equation, they're always going to be positive. The negative just indicates that it needs to be on the product side. Okay, so now we can use this energy just like every other term we use when we're doing stoichiometry. So for example, what if we have 500.0 grams of this hydrogen peroxide, and we want to know how much energy will be released. Okay, so if you look at our chemical equation, this is the amount of energy that will be released if we have 2 moles of hydrogen peroxide. But this problem tells us we don't have 2 moles, we have 500 grams. Well, we can do stoichiometry. 500 grams is how many moles of hydrogen peroxide? So we go to our periodic table. We've done this lots of times now, so hopefully this isn't intimidating to anybody. So in 1 mole of hydrogen peroxide, we have 34.02 grams of hydrogen peroxide. Okay, my grams then cancel out and I'm left with moles of hydrogen peroxide. And if I do this, I learn that I have 14.70 moles of hydrogen peroxide. So again, my chemical equation shows me that I will have 189.2 kilojoules of energy released if I use 2 moles, but I'm not using 2 moles, I'm using 14.70 moles. All right, so let's start with what we know, the 14.70 moles of H2O2. Okay, use our chemical equation to write our ratio. So for every 2 moles of H2O2, I am going to get 189.2 kilojoules of energy. Okay, so this is just stoichiometry. I'm just treating this amount of energy just like any other product. So for 2 moles here, I'm going to get this much energy. Now my moles cancel out. I'm left with my kilojoules of energy as my unit, which is what I want. So I plug in my calculator, 14.70 times 189.2 divided by 2. And if I do all that, I end up with 1,391 kilojoules of energy. All right, so if I'm decomposing 500 grams of hydrogen peroxide, 1,391 kilojoules of energy will actually be released. Okay, so you'll get some practice doing this stoichiometry this week, but hopefully that makes sense. You just list your energy as either, if delta H is negative, it's giving off energy, so it would be listed as a product. If delta H is positive, that means it's absorbing energy, so your delta H would be listed over here as a reactant. And then do stoichiometry and just consider, treat your energy just like you would any other molecule. Okay, we're gonna move on now and talk about activation energy. Okay, so the book uses the example of combustion of paper. We know that for something to combust, we just need to add oxygen to it, right? That's what we've learned. So my paper plus oxygen should yield combustion. All right, but obviously I have my paper here and it is in contact with some oxygen molecules because I'm breathing the oxygen. I know that oxygen's in the air, but my paper is not combusting. So why is that? I have my paper, oxygen molecules are present, but my paper isn't burning up. Well, the molecules making up my paper and the oxygen molecules in the air aren't close enough, aren't coming in enough in contact with each other to actually interact. Okay? So how do we get this paper to combust? Well, we have to light it with a match and start the reaction. All right? So let's think about why using that match starts the combustion reaction. Well, at room temperature, we have oxygen molecules moving in the air, and my paper molecules are just slightly vibrating, and they are colliding with each other. The oxygen molecules are colliding with the paper molecules, but those collisions aren't very violent, and they're not violent enough to break apart any of the bonds in the reactants. Okay, so it goes back to those bond energies. My reactants are my paper and the oxygen. So I have to have enough energy to break those bonds. Well, the collisions happening between oxygen and my paper aren't violent enough to break those bonds. So at room temperature, my paper will not combust. But if we add heat from like a lit match or a lighter, all the molecules start moving faster, and those collisions become more violent and more violent. And those violent collisions actually start breaking the bonds of the paper and the oxygen. And then that's how combustion actually starts. We have to add enough heat that the combustion reaction can start. So any chemical reaction needs enough energy to get the reactants to collide strongly enough together that the bonds can start breaking, okay? And that energy is called activation energy. Activation energy, okay? And it's the energy required to initiate or to start a chemical reaction. All right, so every reaction requires activation energy, okay? But different reactions require different amounts. All right, so if my activation energy is low, if I don't require very much energy to start a chemical reaction, it'll just start up at room temperature, okay? So think about, like you guys have probably all done the vinegar and baking soda. So vinegar and baking soda, even at room temperature, these molecules collide with enough energy to start breaking the bonds and start the chemical reaction, okay? There's enough energy even at room temperature. So this reaction between the vinegar and the baking soda, it needs an activation energy, but the activation energy is so low that even at room temperature, these collisions are great enough to break the bonds. If a chemical reaction has a high activation energy, the reaction may need to get a little kickstart to get it going. And this is like our example of the paper burning. Okay, both of my reactants are present as we're speaking. As I'm speaking, the paper's here and oxygen's here. But the reaction, the combustion reaction, isn't happening because the activation energy is higher. Okay, so the combustion will only happen when I add heat to get these molecules to collide violently enough that they actually start breaking the bonds. Okay, so to visualize this, we use something called a reaction coordinate diagram. And if you're following along in your book, this is on page 428. You'll see an example of this. Okay, and basically it's an XY, and along my Y I have energy in kilojoules, and along the bottom I have, or my X axis, I have the reaction coordinate. Okay, so this reaction coordinate is just, it's almost like time. It's like as the, it illustrates what happens as the reaction proceeds. Okay, so at this end is the beginning of the reaction, and then the reaction proceeds, and here we have the end of the reaction. Okay, so energy graphed against the reaction coordinate. So we can put some values here. We could say this is 100 kilojoules, this is 200, 300, 400, 500. Okay, So when a reaction starts, let's say it starts out at 200 kilojoules, the reaction starts going, okay? And as it goes, here's its activation energy. Now the reaction is ending, and then down here it flattens out again when the reaction is over, okay? So here are my reactants, and here are my products, okay? Because as I travel along the x-axis, this is the beginning of my reaction, okay? I still have my reactions, my reactants, sorry, here the reaction's taking place, and at the end I have my products, okay? So this reaction coordinate is kind of like time passing from the beginning of the reaction to the end. Okay, over at the left I have all my reactants. As the reaction goes, the reactants start reacting, and this increases the energy of the system, and these products start to form, okay? And then for this example, the products forming down here actually decreases the energy in the system. So the energy starts to fall, and the products end up with less energy than what we started with. So at the right, all the products are made and the reaction is done, okay? So if we look at some of these values, let's draw some dotted lines here. Okay, the height of the hill here from our reactants to the peak illustrates our activation energy, okay? And then this difference here, the energy difference between the reactants and the products, represents our change, our delta H, okay? So the activation energy is this hill. In order for the reactants to react, energy has to be supplied, okay? So let's think about this. In our diagram, the energy of the reactants is 200, okay? And the top of the hill is at 400, okay? So what is my activation energy? Well, I had to add 200 kilojoules of energy to get things going. So my activation energy in this case is 200 kilojoules, okay? And remember, we always take our final minus our initial. So our initial was 200, our final was 400. So 400, so 200 equals our 400 minus the 200 units of energy that we started with. All right, what is my delta H? Again, we take our final and subtract the initial. So our final energy when our products are created is 100 kilojoules. Our initial energy when we had our reactants was 200 kilojoules. So my delta H then is negative 100 kilojoules, all right? It's negative 100 kilojoules, so what does that tell us? Our delta H is negative, so it tells us that this is an exothermic reaction. We're releasing energy, right? Our products have less energy than what we started with, so some energy had to have been released. So it's an exothermic reaction. Okay, now reaction diagrams will look different for different reactions. So I'm going to give you some information. It's actually an example in the book, but don't look and let's just see if we can draw this on our own. Okay, draw the reaction coordinate diagram. The book tells us that the reactants start with 100 kilojoules of energy. The book tells us that the activation energy is 500 kilojoules. And we're also told that delta H, or the change in enthalpy, is 200 kilojoules. Say hi, Emmy.
No.
Okay, so given all this information, draw the reaction coordinate diagram. So you guys just try that for a minute on your own and see what you come up with. We know where the reactants start, we know the activation energy, and we know the delta H. Okay, so let's think about this. Reactants start with 100 kilojoules of energy. Okay, so here's my reactants. My activation energy is 500 kilojoules. So that means I have to add 500 kilojoules. So I'm going to get all the way up here to 600. Okay, so my hill is going to go all the way up to 600. And then my delta H is 200 kilograms. Now this is a positive. So my final must have been greater than what I started with. So I gained 200 kilojoules of energy. So my diagram should look something like this. Okay. Let's look at it again. So the activation energy is the height of the hill in relation to the reactants. So this is my activation energy here. Okay. My delta H compares the height, another dotted line here, is this value here. This is the energy my product started with. This is the energy I ended up with my reactants. I'm sorry, said that wrong. This is the energy I started with my reactants. Here's where I ended up with my products. So this is the change of energy between them, okay? My products ended up with a higher energy than my reactants. So what does that tell us? This was an endothermic reaction. My products gained energy. They absorbed the energy because this is an endothermic reaction. Okay, it took 500 kilojoules from where I started. I had to go up 500. So from 100, I had to go up to 600 to get this reaction going. So this is what my reaction coordinate diagram would look like. All right, so hopefully that makes some sense. You'll get some practice doing them this week. I'm trying to think if there's anything else I want to talk about here. Okay, so in the very beginning last week, we talked about spontaneous reactions and that some reactions are spontaneous, some are not. Well, if a reaction is spontaneous, that doesn't necessarily mean it's just going to happen automatically. It's spontaneous if it just will keep going once it's starting. So my example of burning paper is actually a spontaneous reaction because once we get it burning, it will keep burning. It just kind of needed that kickstart. It needed its activation energy. But once it starts, it'll keep burning even if we remove the match. Okay, so activation energy does not necessarily coordinate or correlate with whether a reaction is spontaneous or not. Spontaneous doesn't mean that it will just automatically happen, but it's spontaneous if it will keep going once it's started. Okay, so once I start burning my paper, it will keep burning. So combustion actually is a spontaneous reaction. Okay, we're gonna change gears here a little bit. We're gonna talk about thermodynamics. Okay, it's a big word, but we've actually been talking about thermodynamics already. So thermodynamics is just the study of the relationship and conversions between different forms of energy. Okay, so we've been talking about like potential energy and kinetic energy. All right, we've been talking about this a little bit already. So it's relationships and conversions of energy. And there's two laws of thermodynamics that we're going to talk about. The first one you've probably already heard before in some other class. And we've even referenced it already, just not by name. But the first law of thermodynamics says that energy cannot be created or destroyed, but can only change form. So we can't create energy out of nowhere. We can't lose energy as we go, but the energy can change form. Okay, it can change or convert from potential to kinetic or kinetic to potential. And there's other kinds of energy also, but all right, so we've already kind of been assuming this as we go. You know, the energy absorbed or released in a reaction can't just be lost. If it's absorbed by something, it had to come from somewhere. If it was released, it has to go somewhere. Okay, but before we move on now to our second law of thermodynamics, we need to understand a new concept called entropy. Okay, so last week we studied enthalpy. This week we're going to start studying entropy. Entropy is denoted with a capital S. I don't know why. Okay, so it's the measure of the amount of energy in a system that is not available to do work. Okay, so that's the equation or the definition. The measure of the amount of energy in a system that is not available to do work. So basically what this is trying to say is that some energy in a system can't be captured. Okay, the energy is so unorganized that it can't be organized in a fashion to do work. Okay, so I may have a system that has 1,000 joules of energy in it. Okay, but no matter what I do, I can never use all 1,000 joules of this energy to do work. All right, it could be that I can use 999.9 joules of it, but there's still going to be a tiny bit that the energy is so unorganized it can't be organized enough to do work. Some fraction of this energy simply won't be available. All right, and that's true for all systems. So like a chemical reaction could be considered a system. So in a chemical reaction, there's going to be some energy that's not available to do work, and that's the entropy. Okay. So you can think about it as there's two different types of energy. Okay. There's part of the energy available to do work. And I should say energy in a system. So when we're looking at a system, there's most of the energy is available to do work, but then you're going to have some portion that's not available to do work. All right, and this portion that's not available is the entropy. Okay, so this is kind of unusable energy. Over here, this is usable energy. Okay, so now that we understand this a little bit, we can go to the second law of thermodynamics. And the second law of thermodynamics tells us that the entropy in the universe can never decrease. Okay, so a couple things here. We're talking about the entire universe. The entropy can never decrease. So if we take the universe as a whole, the energy in the universe is never going to become more organized. If anything, it will remain constant or actually decrease. So as time goes on, more and more energy becomes unusable, and less energy becomes usable. So if I looked at the energy in the universe, as time goes on, we're going to have less usable energy and more unusable energy. Okay? And at some point, life is going to cease to exist because of this. There just simply won't be enough energy left to do work. Okay? So things will never become more organized. They will always either stay the same or decrease. All right? When we're talking about the universe as a whole. All right? So the higher the entropy, and again, if you think, it helps me to kind of think of entropy as just disorganized or disorganization. Okay? Entropy is the amount of disorganization. All right? So the higher the entropy, the more disorder. If entropy is going higher, that means whatever we're looking at is becoming more disorderly. Okay? So think about solids, liquids, and gases. Okay? Which of these molecules in a solid, molecules in a liquid, or molecule in a gas, are the most organized? Well, in a solid, the molecules are most organized. They're usually pretty tightly packed, sometimes in a very organized fashion. Okay? In a gas, on the other hand, the molecules are all just bouncing around with a lot of energy, and they're the least organized. Liquids are somewhere in the middle. Okay? So we would say the phase of gas has the most entropy. All right, and solids have the least entropy. All right, again, think of entropy as the amount of disorganization. Solids are much more organized, so they have a lower entropy than gases. Gases are not very organized at all, so they have a lot of entropy. Okay? So, okay, so here we're talking about phases. What if we talk about temperature? And how temperature affects entropy? Well, at a higher temperature, what do we know about molecules? The molecules are going to move faster. right? When molecules are bouncing around faster, that's more disorganized. So we're going to have greater entropy. All right, at a low temperature, molecules don't move as fast. Okay, so there's less chaos here, so we're going to have less entropy, less disorganization. Okay, let's think about, we've talked about phases, temperature. Let's think about the number of molecules. Okay, and if we're following along in our book, sorry, I've moved several pages ahead. I'm on page about 434. The more molecules we have, the more chaos there is, which means the more entropy we have. The fewer molecules we have, there's less chaos, so there's less entropy. Okay, and then finally we can talk even about the distribution of molecules. And for this, you can refer to the picture on page 434 because it shows it pretty well. There's two containers that are identical. The top drawing represents the lower entropy because the molecules are more ordered. They're all in one place. The bottom figure has higher entropy because the molecules are spread all out. Okay? So same number of molecules in each, but the bottom is more disordered. It's harder to track. Where are they going to be? Are they going to be in the first circle, in the second circle, where? So the bottom figure actually has more entropy. Okay, so we talked about the amount of entropy or disorganization for phases, temperature, number of molecules, and the distribution of molecules. So let's summarize it. So we talked about entropy in 4 different cases. Okay, so let's just summarize. High entropy, low entropy. Okay, so this means disordered, chaos. Here we have more ordered, less chaos. Okay, so a gas will have higher entropy than a solid. So the phase matters. A high temperature will dictate more entropy than a low temperature. Again, because the molecules are moving faster in the presence of a high temperature versus a low temperature. More molecules will create higher entropy than less molecules. Think about if you have a family with 10 kids versus if you have a family with 2 kids, okay? The 10 kids are going to create much more disorder and chaos than the 2 kids. And you'll have a higher entropy when there's less ordered distribution versus a more orderly distribution. Okay, so this kind of summarizes gases are much more chaotic, have a higher entropy than solids. Things at a high temperature generally have a higher entropy than things at a low temperature. More molecules basically usually have more entropy than fewer molecules. And a less ordered distribution has more entropy than a more orderly distribution. Okay, so we can analyze the change in entropy just like we did the change in enthalpy. It's a little bit simpler actually because we're not going to get into number of kilojoules and all that. But when entropy increases, so when our final entropy is greater than our initial entropy, final entropy is greater than our initial entropy. Okay, so we end with more chaos than what we started with. Our delta S is positive. Okay, when our final entropy is less than our initial entropy, so in this case things are actually getting more ordered, we're ending up with disorder that's less than what we started with, delta S is negative. Okay, now you may be saying, wait a minute, I thought you said that entropy can never go down. Well, if you remember, I said the entropy of the universe can never go down. Okay, so in a sample, the entropy can increase, but in the universe, entropy cannot. I'm sorry, in a sample, entropy can decrease. In the universe, it can't. So it makes sense if you think about like water freezing, okay? You have liquid, water, and it's becoming ice, okay? Obviously, the molecules in the liquid water, when they turn to ice, have become more orderly, okay? The ice has a lower entropy than what we started with. No, this is gas, but liquid would be the same. Okay, so our final entropy, or our final amount of disorder, is less than the disorder that we started with. Okay, so in a system, in a contained system like this, the entropy actually can decrease. But in the universe as a whole, the entropy cannot increase. Okay, so there's a distinction there. Okay. All right, so when water freezes, let's look at this example a little bit more closely. When water freezes, the entropy of the water actually decreases. When liquid water turns to ice, the entropy actually decreases. But for the water to freeze, the surroundings have to absorb some of the heat that's released. Okay, so for this water to become ice, the surroundings have to absorb that heat that's released. Okay, so the entropy of the surroundings actually increases. Okay, so the entropy of the ice or the water reduced, but the entropy of the surroundings, because it absorbed that heat, actually increased. Okay, so the second law of thermodynamics tells us that the change in entropy for a system, and in this example, my system is the water and the ice, plus the change in entropy of the surroundings, has to be greater than or equal to 0. Okay, and this illustrates an ever increasing entropy. Okay, so the change in entropy of the system, the water and the ice, plus the change in the entropy of the surroundings has to be greater than or equal to 0. Okay, so the final entropy is always going to be positive. Okay, so all of this is actually starting to come together. The temperature at which the release of the water's heat increases the entropy enough to keep this true. The temperature of water that will keep this true is actually 0 degrees Celsius. And that's why water doesn't freeze until it gets to 0. Okay, kind of cool. All right, so this type of reasoning also dictates whether or not a chemical reaction can occur. Okay, so what do I mean by that? Okay, well, the change in entropy of the system, which in this case is the chemicals in the reaction, and the change in S of the surroundings, which is everything else, okay? Unless we can add these two change in entropies and come up with a value greater than or equal to 0, these chemicals will not react, okay? So how do we determine this delta S for a chemical reaction? Okay, we primarily look at two things. All right, we look at the phase and we look at the number of molecules. Okay, and if we can analyze the phase and the number of molecules, it should tell us whether the change in entropy for a certain chemical reaction is positive or negative. All right, so for example, let's look at example 14.5. Okay, so I'm on page 436, or I will be on page 436. It says determine the delta S, or the sign of the delta S for the following reaction. Okay, I have the same decomposition reaction that we keep looking at. 2H2O2 aqueous. It's the decomposition of hydrogen peroxide, yields 2 liquid water molecules plus O2 gas. Okay, so we need to determine, is the change in S, change in entropy, positive or negative? Okay, so we're not actually going to come up with a numeric value. We're just going to say, is this system gaining entropy, getting more chaotic, or is it losing entropy, becoming more organized? Okay, so the first thing we're going to do is look at the phases. Okay, we start out with an aqueous solution. Okay, and we end up with a liquid, which is similar to aqueous, plus a gas. So as we go from aqueous to gas, the molecules are becoming much more disorganized, which indicates an increase in entropy, which indicates that delta S would be positive, right? We're becoming these molecules, because of their phase, the molecules, because of their phase, going from aqueous to a gas, are becoming more disorganized, which means there's more entropy, which means the change in entropy is going to be positive. We can also look at the number of molecules. In the reactants, we have 2. Molecules. In the products, we have 2 water molecules plus an oxygen molecule. So we have 3 molecules in the products. Okay, again, think about a family. If you have 2 children will be more organized than 3 children. So again, we have an increase in entropy, which also says that our delta S will be positive. Okay, so I can pretty assuredly say in this chemical equation of aqueous hydrogen peroxide decomposing into liquid water and O2 gas, that I'm going to have a positive change in entropy. Again, by looking at the phases and the number of molecules. Let's look at another example. Okay, I have 2 carbon monoxide molecules plus an oxygen molecule, both of these in a gaseous state, becoming 2 CO2 molecules, again in a gaseous state. Okay, so let's look at our phases. Again, for all of these, we'll look at phase and the number of molecules. Okay, well, our phase, we have gas and a gas combining to become a gas. Okay, so there's no phase change. Okay, so that's not very helpful. We can't tell by looking at phase. Nothing is changing phase. We can look at the number of molecules. In the reactants, I have 2 carbon monoxide plus 1 oxygen, so I have 3 molecules. Okay, in my products, I have 2 molecules of carbon dioxide, so I have 2 molecules. All right, so is 3 molecules more or less disorderly than 2 molecules? So actually, if I look at my number of molecules, I'm becoming less chaotic, going from 3 molecules to 2. So entropy is actually decreasing. So in this system, entropy is decreasing. In the universe, it's not, but in this contained system, it is. My entropy is decreasing, so my change in S would be negative. Okay, 2 molecules are more orderly than 3. Think of these as families. 2 kids would generally be less chaotic than 3 kids. Okay, so I'm becoming more orderly, so my change in entropy would be negative. Another way to say it is my change in entropy would be less than 0. Okay, we'll look at one more example. Okay, MgCl2, aqueous, plus 2KOH, aqueous, yields MgOH2, solid, so something's going to precipitate out of this, plus 2 NaCl, aqueous. Okay, again, we're going to look at phase and the number of molecules. Okay, phase. I have aqueous reactants becoming solid. Okay, so I have aqueous becoming a solid. So this is becoming more organized, which means my disorder or my entropy is actually going down. Okay, let's look at my number of molecules. I have 1 MgCl2, I have 2 KOH, and then on the product side I have 1 MgOH2 plus 2 NaCl. Okay, so I have 3 molecules in my reactants, 3 molecules in my products, so the number of molecules is the same, so that doesn't really help us. So I can just rely on this then, that because I'm going from 2 aqueous solutions to 1 aqueous and a solid, my system here is actually becoming more organized, and so my entropy is reducing. So my change in entropy then is actually greater than 0. Okay. I think something on my notes is written wrong. Sorry. My change in entropy again is less than 0 because my final entropy, hold on. Yes, my final entropy, I'm more organized than what I started with. So in both of these cases, my entropy's going down, which means my change in entropy will be less than 0. Okay? All right, so that's as far as we're going for this week. Okay, so for this week, we're just going through entropy, just trying to determine if it's positive or negative. Okay, so we'll pick up where we left off last week. You'll go through comprehension check 10. I am assigning some review questions each week, and then at the end of this chapter, I'm going to assign the extra practice problems or the extra problems on the website just to give you more practice with all this. So again, I know this is a little bit difficult material. That's why we're moving a little bit more slowly. Make sure that you're reading the book. And if you need extra help, there's all kinds of things online too that will help. If you have questions, put them on Google Classroom and all that. You guys know the drill. So I hope you guys are doing well. I hope these videos are working okay. And we'll just look forward to meeting together next week again.